Welcome to the second lecture of electric circuits. In this lecture, we are going to see some basic network theorems. So, starting with superposition theorem. So, before understanding its statement, let's solve one question on this to get a better idea of this theorem. So, we have a circuit shown here, and you have to find the current flowing through this R1. So in this case we have two sources, one voltage source 6 volt and another is current source. So according to superposition theorem, we'll find the response of each individual sources first, then we'll combine this. So we'll start with this voltage source E. For calculating the response of this voltage source, we will open the current source present here. So now we have this 6 volt voltage source, and here R1 and R3 are in series and this whole is in parallel with R2. So R equivalent is R2 in parallel with R1 plus R3. So by putting their value, we get R equivalent is equal to 2 and E is equal to IR. So I is equal to 3 ampere. So I is equal to 3 ampere and it is flowing in this direction. And now we have to find the current flowing through R1 as it was asked in question. So here we are going to use the current division rule, which we have studied in first lecture. So current flowing through R1 is first total current, which is 3, is divided by the total resistance, and then if you want to find the current flowing in this branch, then you have to multiply it by the resistance of other branch. So we multiply it by R2, and so 1 ampere current is flowing in this direction due to this voltage source. Okay, so now we will see the current flowing through R1 due to this current source. See, in earlier case I have opened this current source, but now here I am shorting this voltage source. Why? Because except from the source which is being considered, the other voltage source is short circuited and current source is open circuited. So this is short, and as a result the current will not flow in R2. So this will be the equivalent circuit, and now by current division rule you can find the current flowing here in R1. So I double dash, which is the current flowing through current source, is total current. Total current was what? 3 ampere upon total resistance, which is now R1 plus R3. And then since you want the current flowing through R1, so we will multiply this by R3. Therefore, we get 2 ampere. So here 2 ampere current is flowing in this direction due to current source, and due to voltage source 1 ampere was flowing in this direction. So the total current flowing through R1 is 2 minus 1, which is 1 ampere in this direction. You can solve this question using KVL and KCL also, but sometimes using superposition theorem makes your calculation easy, as you can see here. Okay, so now let's get to its statement. The response in any element of a linear, see these are the terms, linear bilateral RLC network containing more than one independent voltage or current sources is the sum of the response produced by the sources, each acting alone. See, in that question, first we assumed voltage source and ignored the current source, and in second case we consider current source and ignore the voltage source, and then in the end we combine the total result to get our answer. So here the total result is the sum of the response produced by the sources, each acting alone, when. Now what we do for the other voltage and current sources? As you have seen, all the independent voltage sources are short-circuited or replaced by their internal impedances, and all the current sources are open-circuited or replaced by the internal impedances. All the dependent voltage and current sources. See this term, all the dependent. You will understand this dependent term in few minutes. So whenever they are present, then they remain as they are. Therefore, these sources are neither short-circuited nor open-circuited. You don't have to touch them. We just consider the independent voltage and current source. This theorem is not applicable for the network containing single independent voltage or current sources, because if you have single independent source, then there is no need to apply this. This theorem is used for multiple independent voltage or current source. Then if any non-linear element is present, non-linear element means V is not proportional to I. Then unilateral elements. Example of unilateral elements are diode, PN junction diode. So this theorem is not applicable to non-linear parameters also. For example, power. As you have seen that in question we have to find the current flowing through R1. So you can find I, current. Through this theorem you can find voltage also, but you cannot find the power because it is non-linear, as power is proportional to square of voltage and square of current. So when you have to find the power, then first we find the voltage or the current, and then from the voltage and current we find the power. But we don't apply this theorem directly to find the power. See, all these conditions are very important, including the statement of this theorem. It is asked in many examinations in 1-mark question, like state true or false that this theorem is applicable for single independent voltage source or not. Okay, so we have this one more question here. So there is this network N, which is linear network and contains only resistor. And also here we have two current sources, means more than one. So we can apply superposition theorem in this question. So here it is given that I1 is this, I2 is this, then Vx is 80, and I1 is this and I2 is this, then Vx is 0 volt. You have to find this voltage Vx when I1 and I2 is 20 ampere. So first we'll consider the response through this current source I1. Then what we'll do, we'll open this I2. Since it's a resistive network, therefore we can write Vx1, which is the response of current source I1 when I2 is equal to 0. So this is equal to I1 R1, and similarly when I1 is equal to 0, then the response of current source I2 is equal to Vx2 is equal to I2 R2. So by using superposition theorem, the total response Vx is equal to Vx1 plus Vx2, which is this. Now we will put these two conditions here and we'll solve. We will get the value of R2 and R1, and we put the R1 and R2 value in Vx. So the total Vx is this. Now the thing was asked, we have to find the value of Vx when I1 and I2 is equal to 20 ampere. So we will put I1 I2 is equal to 20 here, and we'll get this 150 volts. So this is our answer. See, here we don't know the network, how this I1 and I2 are linked, and where we are finding the Vx. Here we just have two sets of data, and using this theorem we can find the value of Vx for any value of I1 and I2. See, in network theorems we have three most important theorems. One was superposition theorem, which you have seen. Second is Thevenin and Norton theorem. This is very, very important. And third is maximum power transfer. We'll see that later. So let's start with Thevenin and Norton theorem. So here the two terminals A and B have voltage V between them, and the current I is flowing. And then there is a network N, then this N network can be written in Thevenin's model like this and Norton's model like this, where VOC is the open circuit voltage between the terminals A and B when I is equal to 0, and ISC is the short circuit current flowing between the terminals A and B when both are short circuited, means when B is equal to 0. And the equivalent impedance is the impedance seen from this terminal A and B. You can also find equivalent impedance by dividing VOC by ISC. Both theorems are same. In fact, they are just dual of each other. So let's start with Thevenin. Now, here also you have to note this basic terms which can be asked in question form in examination. So, a linear active RLC network which contains one or more than one. See, in superposition theorem, it is applicable only when more than one independent voltage or current sources are there. But in Thevenin's theorem, even one independent source will work. So here, a linear active RLC network which contains one or more than one independent or dependent voltage or current sources can be replaced by a single voltage source VOC in series with the equivalent impedance Z equivalent. See, this is voltage source VOC and its single equivalent impedance Z equivalent is in series with the VOC. Now for Norton theorem, the conditions are same: linear, active, one or more than one independent or dependent voltage or current sources. But this can be replaced by a single current source ISC in parallel with the equivalent impedance Z equivalent. See, the difference between these two theorems is this statement: voltage source VOC in series with the Z equivalent and current source ISC in parallel with the Z equivalent. So what is the equivalent impedance Z equivalent? How are you going to find this? We are going to some similar concept as we have seen in superposition theorem. So here the equivalent impedance Z equivalent between the two external terminals, we will find the equivalent resistance when all the independent voltage sources are short circuited or replaced by the internal impedance. Current sources are always open circuited or replaced by the internal impedances, and we do not touch any dependent voltage and current sources. They remain as they are. Therefore, these sources are neither short circuited nor open circuited. For pure resistive network, Z equivalent in Thevenin's model is also written as RTH, and for Norton's it is RN. You can denote it by anything, but usually ZTH or ZN is preferred. Okay, the theorem is always applicable irrespective of the nature of the components, like whether they are reactive or resistive. As you have seen that it includes the term RLC network. So the nature of the components can be anything reactive or resistive. Nature of voltage and current sources. This theorem is applicable if the sources are AC or DC. So where it is not applicable? Whenever you have non-linear elements or unilateral elements such as PN junction diode. Okay, so let's understand this theorem by solving this question. So there is this network. You have to find IL current which is flowing through this load resistance of 2 ohm. Also, you have to find the equivalent impedance RTH between AB and the Thevenin's equivalent voltage and Norton's equivalent current source. So first we will calculate this RTH. For this, we will short all the voltage source and open the current source. So when you short this voltage source and open this current source, then you will get this network. And now the Z equivalent is 1 plus parallel combination of 4 and 12. So it is 4 ohm. Okay, now for calculating VTH. What is Thevenin's equivalent voltage VTH? It is also written as VOC. It is the open circuit voltage between the terminals A and B. Since it is open circuited terminal, therefore no current will flow, means I is equal to 0 here. So the total current 2 ampere will flow here. And then let us assume that I is the current flowing in this direction. Then the total current flowing through this 12 ampere is I plus 2. Then the open circuit voltage between A and B is equal to 12 into this voltage. So 12 into I plus 2. So we'll apply KVL in this loop. So 32 volt is equal to 4 into I. Then here all current is in the direction in which we are moving. So we'll use plus 12 into I plus 2. From solving this, we get I is equal to 1 by 2. Therefore, the open circuit voltage is VTH is equal to 30 volts. Now for ISC. What is ISC? ISC is the short circuit current. The current flowing when A and B are short circuited. So here voltage is equal to 0 and ISC is flowing in this direction. So the total current flowing here would be 2 minus ISC when you apply KVL here. Then you will understand that total current going to the node is equal to total current moving from the node. Therefore, this current is equal to 2 minus ISC. And let us assume that current I is flowing in this direction. Then the total current flowing in this 12 ohm resistor is I plus 2 minus ISC. Now we'll apply KVL in this loop. Then we'll get 32 volt is equal to 4I plus 12. Then the current flowing, which is 2 plus I minus ISC. So we got this first equation. Then second, there's another loop here, which is this loop DC AB. So we'll apply KVL in this loop. 32 volt is equal to 4I, and then you don't have any element here, and then here we have 1 ohm and current ISC is flowing in it, therefore plus ISC. So this is the equation. Now you have this 2 equations and 2 variables. So we'll solve this, and therefore ISC is equal to 7.5 ampere. Instead of going this long method, you can also use this method which we have seen, that Z equivalent is equal to VOC upon ISC, and thus by putting the value of Z equivalent and VOC, you can find the value of ISC, which is VOC upon R equivalent, which is 7.5 ampere. So this is our Thevenin's equivalent model, and now we will find the current flowing through RL, which is IL, by applying KVL. So 30 divided by 4 plus 2 is the current flowing, which is 5 ampere. Also we can see its Norton equivalent is this, and now the current flowing in 2 ohm by using current division rule, 7.5 divided by total resistance, which is 4 plus 2, and multiplied by the resistance of other branch, which is 4, we get 5 ampere. So you can see by using the Thevenin or Norton equivalent model, you can find the load current so easily. Therefore, This equivalent model is used to simplify your question. Okay, now we have this another question, which is you just have to find the Z equivalent. So why I use this question is because it has this dependent voltage source. In case of dependent voltage source, how you will find this Z equivalent? So first you will open all the current source and short all the voltage source as you have seen, and then you will find the resistance between A and B. Sometimes this dependent voltage source gets completely vanished by these two steps, but sometimes it doesn't. So in those cases we'll use this method. So what we do is we apply 1 volt battery here, supplying current I. Then the equivalent impedance between A and B is voltage upon current, and since voltage is 1 volt and battery current is I, therefore the equivalent impedance is 1 upon I. Now we'll solve this question and we'll find the value of I. But remember, before applying this, you have to short all the voltage and open all the current sources. Now since you know the concept, now this is just the equation. So first we'll apply KVL in FCDE. Where is FCDE? This is FCDE. So we are going to apply KVL here. So we have made some assumption here, like current I1 is flowing in this direction. You can choose any direction. I'm choosing direction according to my convenience. That's it. So I1 is flowing in this direction and I2 is flowing here in this direction. Since I2 is flowing here and I1 is flowing here, therefore total current flowing here would be I2 minus I1. And then at this point I2 minus I1 is coming. I1 is coming from here and I is coming. Then the total current flowing here would be summation of these three currents, which would be I2 plus I. So now we'll apply KVL in this loop. So 4I2 is equal to 2I2 minus I1 plus 6I2 plus I. Then you'll get this equation. Also you can see that Vx is equal to minus 4I2. Why? Because in any resistive element, when current is flowing in this direction, then the polarity of voltage drop is this. Therefore I2 is flowing this and this is 4 ohm. Therefore voltage drop would be 4I2. But here it is given that Vx is in opposite polarity. Therefore Vx is equal to minus 4I2, or 4I2 is equal to minus Vx. For any passive element, means which is not current source or any voltage source, when current is flowing in this direction, then voltage drop occurs in this direction. And when current is flowing in this direction, then voltage drop occurs with this polarity. Okay, now we'll apply KVL in this loop. So here 2Vx is equal to, see here the current is flowing in this direction, but we are moving in opposite direction. Therefore we'll add minus sign. So 2Vx is equal to 2I2 minus I1. Therefore we get another equation. So now in the end we'll apply KVL in this loop. Therefore 1 volt is equal to 2I plus 6I2 plus I, which is this. And now by solving all this 1, 2, 3 and all this equation, you will find that I is equal to 1 by 6 ampere. You can pause this video to see how this I is derived, because this is all mathematical operations only. So now I is equal to 1 by 6 ampere, and as we know Z equivalent is 1 upon I. Therefore 6 ohm is the equivalent impedance between the terminal A and B when the network contains dependent voltage source. So this is how you're going to deal when there is dependent voltage or current sources. Okay, so this is the last important theorem, which is maximum power transfer theorem. So according to this, in order to transfer the maximum amount of power from source to load, the load impedance must be complex conjugate of the source impedance. Means ZL should be complex conjugate of ZS. So let us assume ZL is RL plus XLJ and ZS is RS plus JX. Then its complex conjugate would be RS minus JX. So in order to transfer the maximum transfer theorem, these two should be equal, means that the source and the load should have equal resistive part. They should also have equal reactive parts also, but their signs should be opposite. As you can see here it is plus and here it is minus. So if source is inductive, then the load must be capacitive and vice versa. To apply the maximum transfer theorem in any given network, first you have to transform that network into its equivalent standard Thevenin's model or Norton model, whichever you prefer, but we prefer Thevenin's here. The maximum power transferred to the load is only 50% of the total power generated. Means the maximum power which you can give to the load is only 50% of the total power generated. This theorem is applicable irrespective of the source, whether it is DC or AC, and irrespective of the nature of the source and the load. Means it can be resistive, reactive, or any RLC combination. Okay, now see, this is the Thevenin's model. This is the VOC voltage, and this is a Z equivalent, which we have denoted by ZS, and its value is RS plus JX. And this Thevenin's model is supplying current to the load, which is RL plus JXL. So first we'll study the general case. When XS is this and ZL is this, for maximum power transfer, ZL should be complex conjugate of ZS. This we have seen that RL should be equal to RS and XL should be equal to minus XS. So here if we find the value of I, which is the current flowing here, so it is equal to Vs upon ZL plus ZS, and power transfer to the load is I square RL. Why RL, why not ZL? Because it is the power, it is the active power transfer to the load, means power absorbed by the load, and resistor absorb the power. Whenever we have the term of power dissipation or power absorbed, then usually resistor is present. Therefore, PL is equal to I square RL. We'll put the value of I here, then we'll get this. And now we apply this condition for maximum power transfer. Then the maximum power which can be transferred would be this V square upon 4RL. So second case is that if the load impedance is full resistive, then it is equal to the magnitude of source impedance, which is under root of RS square plus X square. Now third case, when ZL is resistive and ZS is also resistive. Pure resistive case means DC case. Then it's simple, RS should be equal to RL for maximum power transfer. In some examination, people ask this question, find the value of ZS for maximum power transfer. See, this theorem is applicable when source impedance is constant, it is not variable, and only ZL is variable. But if ZS is variable, then what? So what is the value of ZS for maximum power transfer? So as you can see that for maximum power transfer, here I should be maximum, and I is what? Vs upon ZL plus ZS. So the value of ZS for which I is maximum, what would be? It would be ZS is equal to 0. At this value, I would be maximum and therefore I square would be maximum. So the power transferred would be maximum. But this is only the case when the source impedance is variable, because in this theorem we have assumed that source impedance and source voltage are not variable, only the load is variable. Okay, so we have completed our important theorem. Now these theorems are just for your knowledge. They are not so important. So let's start with Tellegen's theorem. So in any network, total instantaneous power absorbed by various elements in different branches of the network is always equal to 0. It means that if B is the number of branches and Vk is the branch voltage, Ik is the branch current, then the summation of all the power absorbed by various elements in different branches should be 0. In other words, in any network, total instantaneous power delivered by various voltage and current sources. Here it was mentioned elements, but now we have classified them in active and passive. Like in any network, total instantaneous power delivered by various active elements, which is voltage and current sources, is always equal to total instantaneous power absorbed by various passive elements, means resistor, inductor, in different branches of the network. So this theorem is applicable irrespective of shape of the network, type of the element contains, and value of each element. This theorem is valid as long as the KVL and KCL equations are applicable to the given network. So let's start with the resistor, which we have seen earlier also, that the power absorbed is VI, where I is the current flowing, and when I is flowing in this direction, then the voltage will develop polarity like this, and therefore the power absorbed is VI. Okay, if there is any voltage source V such that the I is flowing into its positive terminal, then this voltage source is actually absorbing the power, so VI. In other words, it is delivering the power minus VI. And now if the voltage source is supplying the current, means current is going from the positive terminal, then it is delivering power, and thus power delivered is VI. Since it is delivering power, therefore power absorbed is minus VI. Minus sign here indicates that it is not absorbing, it is delivering. Okay, so this is the circuit. It may be a little bit clumsy, but let's see. So here this is voltage source V and supplying I1 current. Then there is a resistive network, as you can see, and you know its value. You know all the value of the current flowing and the voltage developed, like I2 V2 in R2, I3 V3 in R3, and similarly then the total power absorbed, which is PA. So who will absorb the power? Passive elements. So it is V2 I2 plus V3 I3 plus V4 I4 and so on till V8 I8, and then total power delivered. Who will deliver the power? Active element. So it is V and I1, and according to Tellegen's theorem, this power absorbed is equal to power delivered. It is basically another form of law of conservation of energy. So we'll equate these two equations, and then we can find any value which is asked in any question. If we see the first definition of the Tellegen's theorem, which is here, this, that the total instantaneous power absorbed by various elements in different branches of the network is always equal to 0. So according to that theorem, we will add all the power absorbed by all the elements, means both active and passive. So this was the power absorbed by the passive element, and now power absorbed by the active element, as we have seen by sign convention, that it would be V1 I1, and then this equal to 0. This is the Tellegen's theorem. See, these two equations are same. For this theorem, you just have to understand this sign convention, then it's very easy to apply this, but its application is very rare, only it is asked theoretically. Now we have this reciprocity theorem. So in reciprocity theorem, in a linear bilateral single source network, see, these are like adjectives which you have to remember. Excitation to response ratio is constant. irrespective of the position of the excitation or response, when the position of excitation and response are interchanged. The basis of this theorem is the symmetry of the impedance or the admittance matrix, which you will understand in two-port network what is the impedance matrix and admittance matrix. But this is basically on the symmetry of those two matrices. Okay, so where it is not applicable? Whenever we have non-linear element or unilateral element like diode, or multiple independent or dependent voltage or current sources, even if there is a single dependent voltage, then also this theorem is not applicable. So this is the impedance matrix, we denoted by Z. These are the conditions for reciprocal network. You will understand this in two-port network better, but you can just have a basic idea from this. So let us assume that there is a network N where V1 is the excitation and its response is I2. It is given I2 current in some element. Then here excitation upon response is V1 upon I2. Now in this case the network is same, but we have interchanged the position of excitation and response. So now excitation upon response ratio is V2 upon I1. So if N is a reciprocal network, then according to reciprocity theorem, excitation upon response is constant, which is V1 upon I2 is equal to V2 upon I1. Okay, so we have now this last two theorems, Milliman and dual Milliman's theorem. So Milliman theorem is just an extension of Thevenin's theorem, and it is useful whenever there are large number of voltage sources. Means when there is more number of voltage sources, then we apply this Milliman theorem, and it is applicable only when the given network can be rearranged in standard format. Standard format means Thevenin's model. So see, this is the Thevenin's model, and whenever there are many such models are added, then it can be represented by a single Thevenin's model containing E and Z. Then the value of E is E1 upon Z1 plus E2 upon Z2 and so on, divided by 1 upon Z1 plus 1 upon Z2. And in summation form you can write this, and Z is 1 upon summation of yi. Y is what? 1 upon zi, means y is admittance. There is this special case, if one of the impedance is 0, I've considered here Z2 is 0, then the equivalent circuit of this whole model would become this. So now this will help you in solving questions, but again this is used very rare, but you should know it. Now dual Milliman theorem. Milliman's theorem was extension of Thevenin's theorem, but dual Milliman theorem is extension of Norton theorem, and the conditions are same. These are used where large number of current sources in any given network, and this theorem is applicable only when it can be rearranged in standard format. Standard format for dual Milliman's theorem is Norton model. So you can see that various Norton models are added, and now you have to find equivalent Norton model with the current source I and impedance Z. Then Z is equal to Z1 plus Z2 plus so on, and I is equal to I1 Z1 plus I2 Z2 plus to the IN Zn divided by Z1 plus Z2 to Zn. Here we have one special case when Z1 or any specific impedance is infinite, means open circuited. Then the equivalent circuit would become this. Then only current source would be present, no impedance. You can derive this model by applying this Z1 is equal to infinite here and here. You will find that Z would become infinite and I would become I1. Okay, so now we have completed all our theorems. Now there is one small topic left, which is the duality between the two networks. So we'll understand how to draw the dual network. See, here we have this network N1, which is a series RLC circuit. So we'll apply KVL here. Then RIT plus L di by dt. Why? Because this is an inductor. Plus 1 upon C integration of IT dt is equal to Vt. This is when we apply KVL here. And now for N2, which is the parallel RLC circuit, so voltage source will become the current source, resistor will become conductance, and the current will become voltage, inductor will become capacitor, and capacitor will become inductor. We'll see this in separate table. But for now, here we have applied KVL and here we'll apply KCL. So here I dash t, when we apply KCL in this node, then the current entering this node is equal to current leaving this node. So I is equal to Vt upon R dash, but since it is G dash is what? Conductance, which is 1 upon R dash. Therefore, Vt into G dash plus C dV by dt and plus 1 upon L dash integration of Vt dt. So for any network N1, N2 is its dual network. Then here the voltage will become current and current will become voltage. If N1 is series circuit, then N2 would be parallel circuit. If there is loop in N1, then we will have node in N2. If we apply KVL in N1, then we apply KCL in N2. Resistor will become conductor, inductor will become capacitor, and capacitor will become inductor. Voltage source will become current source. So the network N1 and the network N2 are dual of each other. Duality doesn't mean that they are equivalent. So these two networks are not the equivalent networks, and therefore the network N1 cannot be replaced by its dual network N2 and vice versa. So you can say this is disadvantage also. If we know the response of any network in terms of the current variable for specified excitation, then we can write the response of its dual network in terms of its voltage variable for similar excitation directly by inspection without actually solving it using the transformation shown in the previous table, this transformation. So if we have a network and it's very complex, we are unable to find its response, then we find its dual network and we find the response with the similar excitation, and then by introspection we can find the response of the original network. So this is the use of duality. Now we have this question. We have to find the dual network of this network. It contains voltage source, resistance, inductance, capacitance, everything in it. So how you're going to solve this? So as you know that here loop will become node here. So here how many loops are there? A, B, C, D. So I have mentioned them as a node. Then I have made this reference node here. Now we are going to join each node. So now we have joined this A to reference node. Therefore, this voltage source will become current source. See this. Since voltage polarity is plus here, current will be flowing here. Therefore, I have applied current source in this direction. And then this is series connection. Therefore, in its dual network, it becomes parallel connection. And this is 1 ohm. Therefore, its value would be 1 Siemens, which is conductance. Now this A and B are connected by 2 ohm. Therefore, here it would be 2 Siemens. Then B and C are connected by 4 farad capacitor. Therefore, here it would be inductor of 4 Henry. And then 3 Henry inductor between B and D. So it's 3 farad capacitor here because inductor becomes capacitor. 5 farad capacitors between C and D, which means here it would be inductor of 5 Henry. And now what are left? This 6 ohm and 7 farad. So now D is connected to reference node. 7 farad will become 7 Henry. and 6 ohm resistance will become 6 Siemens conductance. So this was our network, and this is its dual network. I have drawn it more neatly, and now you can compare this. Voltage source become current source, 1 ohm becomes 1 Siemens, 2 ohm become 2 Siemens, 3 Henry becomes 3 Farad, 5 Farad becomes 5 Henry, 4 Farad becomes 4 Henry, and so on. So this was all about network theorems and duality. You can post your queries in the comment section. We will further understand this subject in next lecture. Thank you.